We present an approach for evaluating geometric content similarity between 3D point sets or range images for indoor or structural type settings. We quantify how similar two given 3D point sets are. Amongst a given set, we identify the most similar views. We further ascertain whether the similar views pertain to the same physical scene or not. The approach does not make use of any priors, additional information, or assumptions on scene structure. We address the problem in a geometric retrieval setting which is minimally restrictive. While high-performing retrieval approaches exist, they have been reliant on appearance. Given a query 3D point set, we derive a discriminative and robust signature for it. This is done by capturing geometry at macro scales, derived in a completely viewpoint-invariant fashion over patch neighborhoods. The geometric signature can then be used for retrieval from an unordered database or a repository of assorted signatures. Obtained retrievals have similar structural content as the queried point set. A geometrically diverse subset is then selected from it. The diversified retrievals can then be utilized as per task. For instance, they could be presented to a user for selection and further processing. They could also be spatially validated to determine whether they pertain to the same physical scene or not. This can be useful in multiple ways. For instance, recognizing places, or localizing or relocalizing with respect to the environment. This could be used for free-form reconstructions without relying on spatial or temporal contiguity of data frames. This is in contrast to, for instance, SLAM approaches on 3D data, which require most consecutive frames to be proximal. The approach outperformed purely geometric baselines. It was about twice as successful in relocalization experiments. It also compared well with state-of-art RGB and RGB-D approaches. It did not require additional information such as reconstructed workspace models, posed ground truths, or contiguous training frames. It exhibited good generalization and robustness. A single set of learned models performed well across the datasets. Results held up well when the database was scaled up, or was made much sparser. This is indicative of the approach's robustness to viewpoint changes, partially overlapping content, and occlusions. We also established that significantly richer workspace reconstructions can arise when reconstructing from a diverse set of viewpoints.